In this video, we're going to talk about precision timers. Now, there is most of the circuitry for microprocessors and devices that are running clocks that are fast. And with our description of fast is anything that is larger 500 kilohertz. That means 500,000 cycles per second. We use typically we'll use crystal oscillators to do that, and these are crystals that vibrate at a very precise frequency, and their oscillation is amplified and used as a clock. Let me back up and kind of talk about what a clock is. Clock is a signal that is a square wave, and in our case it basically swings from 0 to 5, and it gives us more or less the rhythm or for our circuitry. We work off of that clock. We get all synchronized to either when it goes up or when it comes down, and all the circuitry is designed such that performs their task precisely on the assigned side of clock, either on the rising edge where the clock is going from 0 to 5, or on the falling edge, which is when it's coming back down. This is one cycle here, and this is the on time, and this section is referred to as off time. So when we say we have a frequency of 500, let's say kilohertz, we are basically saying that this signal will have 1 over 500 times 10 to the 3, which basically says every 2 milliseconds, every 2 microseconds, which is every 2 times 10 to the minus 6 second, we have a complete pulse. So this is called the period, just a refresher. This is called the period. This is called the frequency. So when you go to buy your computer and they say your computer is running at 4 gigahertz or whatever speed, they're giving you the frequency. So if your frequency for your clock is 4 gigahertz, that means that that's 4 times 10 to the 9 hertz or cycles per second, which means your period is going to be basically 1 over frequency is 1 over 4 times 10 to the minus 9 second. Pretty fast. Okay, so those are crystal oscillator. You have to basically have purchase one that is for the appropriate frequency you want to work with. Now, if you're working with a circuit that is less than 500 kilohertz, the clock requirement is less than 500 kilohertz, there are some devices there's this one device that's great for this. It's the name is 5.5 timer. It's kind of a limiting name for it because it is a very broadly used for many different activities. There are multiple manufacturers who produce it, and I just wanted to show you the data sheet. There's a lot of pages here, but this is a precision timer, and usually referred to as 555 timer. It's got many different operations, and it comes in multiple packages. The one we typically use is the DIP package. This one up here is dual line plastic package, just because of ease of use in a laboratory environment. If you were pulling a manufacturer, of course we use one of our surface mounts, so it'd be easier and faster to implement when we have robots and things like that. You're welcome to read this data sheet. It gives you a lot of different information about how to use this thing. Gives you some functional block diagram of how this device works. This is beyond the scope of our conversation here. It talks about power consumption and all of that about it. And then at the very end, it's getting to be less common, but in the early days of these devices, you would get lots and lots of information about their performance with various kinds of power consumptions, various kind of temperature, and various levels of voltage and current that they're given, and all of that. But here, this is called the application notes section or application information. One of the operations this has called a monostable, where you give it an input and it triggers either a longer or shorter pulse based on what you trigger in and what values of resistors you picked for it. The other, so that's not what we're interested in for this. A-stable is more or less what we're interested in, and we're gonna set it up a little later on and talk about how you select it such that you would have a clock coming out, a square wave at your frequency coming up. And then of course there are other ways you could set this up, and we will just let you, if you're interested, to read the material in this datasheet to learn all the different ways you can set this device up. Let's go ahead and go back to our board. So the one we are focusing here is the 5-5 timer. Okay, and let's go ahead and take a look at how we would set it up. And here's just some cutout from the data sheet we just observed. Again, this is the part as we use it as a in the DIP dual inline package format, and then this is how we're going to set it up. Now, when you first look at this thing, this thing has 8 pins, 1 through 4, 5 through 8, and output comes out of 3. And there's really no input going into it other than power. So we're gonna put in plus 5 volts here for VCC. And notice the VCCs, the connections here are pretty obvious. 5 volt goes to 8, then goes to this capacitor that's connected to ground. This is commonly referred to as a decoupling capacitor, and its job is decoupling. Capacitor's job is to clean up the signal so it doesn't have ripples on the power. Okay, and then these three elements, this resistor between 7 and 4, and 7 and VCC, and then 7 and ground, and 2 and ground, 2 and capacitor to the ground. So these 3 elements are the elements that really control how fast the device is running. This is simply a pull-up resistor, so it's always 1K regardless of what you're doing with it. One thing to notice, this is only indicating that reset has to be high for it to run. This is called active low. So this is this little bubble up here telling you if you make the reset 0, you are resetting. If you make it 1, reset is inactive. Okay. When you're wiring this, one of the most common things I've seen is people forgetting to make these connections because they're outside of the schematic. Remember, we do this to simplify your schematic when things just simply can be put in here. The biggest one I see is ground being missed. So when you're wiring, and make sure that doesn't happen to you, and make sure you connect it once so you can get a nice clock coming out of it. Okay, so now let's say, what are the formulas that allows me to figure out how fast I want to run? Remember, this output will be a square wave, on and on, right? So this part is referred to here as T high, okay? And if resistors are in ohms, capacitors in farad, what you're going to happen is that roughly, I'm going to use 0.7, this is 0.69, but we'll use a 0.7 just to approximate that. 0.7 times RA plus RB times C, that tells us how long it's going to be high. And the low side is going to be T low, is going to be 0.7 times RB times C. Okay, again, resistors have to be in ohm, and this has to be in farad. Okay, no, let's take a look at, let's say someone comes up to you and gives you, they say, I have set this up, and for my configuration I have set it up such that RA is equal to 10K, and RB is equal to, let's say, 5K. What does my pulse look like? You say that's pretty simple. I'll take this value so that I need to have them in ohms. So this is what I need, and hopefully you realize that, oops, 5,000. And you realize that they haven't given you the capacitor, so we need to ask what capacitors you want us to use. And let's say they say the capacitors you need to use is gonna be 10 microfarad. You say, okay, 10 microfarad, I have to turn that into a farad. That would be 10 times 10 to the minus 6 farad, which when I convert it is going to be 10 to the minus 5 farad. Okay, so now that we got this, we can take this piece of information and plug it back up here, which tells us, okay, it's 0.7, RB is 5,000 times 10 to the minus 5. Great. So if I multiply this out, this is gonna give me 3.5 times 10 to the 3, right? So so what I'm gonna end up here is that's gonna be, well, I'll just write it, is gonna be 3.5 times 10 to the minus 2 second for the low time, or roughly 35 millisecond. We can write that 35 millisecond. So that's how long it's low. And then the high part is going to be 0.7 times 10,000 for RA, 5,000 for RB. Multiply this whole thing by 10 to the minus 5. So if you do this, then I can do that in my head. But anyway, it's going to be 0.7 times 15,000 times 10 to the minus 5. Take a break, go do the count. Okay. So when we multiply this back out, it's going to be 10.5 times 10 to the minus 2 second, which is 105 millisecond. So now let's just carry this forward. So now we've got a square wave where the low time is 35 millisecond. Actually, it's probably not quite drawn to proportion. Let me redraw this one to proportion. And the high time is 3 times as big, 105 millisecond. Which means the period for this pulse is gonna be 140 millisecond is the period, which means the frequency is gonna be 1/10 to the 3 divided by 140. So approximately 7 hertz. Okay. Of course, as you make the capacitors bigger and resistors, as you make the capacitors smaller and the resistors smaller, the frequency is going to keep going up. So this one is going to be basically pulsing 7 times a second for us. I think that brings us to the end of this particular presentation, where now we're able to use these two equations, this one and this one, if somebody tells us they want a certain frequency, now we can pick RA, RB, and RC to meet those frequencies. Or if we know what the values of RA, RB, and RC are, then we can go ahead and tell them what the frequency is going to be. So if you hook up the 5 this way, these are the two equations that we have. That's about all there is to it. Let's do one more. Let's say if someone comes to you and say use 555 timer to design a clock generator with frequency, let's say frequency of let's go up high to, let's say, 100 or 1,000 hertz. Okay, and duty cycle of, let's say, 40%, or I'll make it 60%. Okay, so if that's what they're asking, I said, what would we do? So first thing is to understand what they're asking. They're basically asking, you want to design, okay, design a clock, a circuit that gives us a clock such that the low time, the high time over the period, this is the period, this is the T high, over the period is 60%. That's what that means, and T low is here. So okay, so first thing we know is that T high must be equal to 60% of the period. That's one thing we know. The other thing we know is that T, capital T, is 1 over frequency. They told us it's 1 over 1,000 hertz, which means this is going to be 1 millisecond. Or if you let's put everything in second, that's 10 to the is 3 seconds. Okay, the other, so that basically tell us that T high has to be 60% of that, so it's going to be 6 times 10 to the minus 4 second. Okay, if you know T high, we know how long the total period is, the rest of the period, so T low is going to be basically whatever the period is minus the piece that is not high, which tells us 4 times 10 to the minus 4 second. Okay, now since they want us to use a 5-5 timer, from earlier we know T high is going to be equal to 0.7 times RA plus RB times C, and we know T low, T low has to be 0.7 times RB times C. Just double check. Here is the equations, and those are right. Okay, so I have a bunch of information. I have this information. What I can do, since I know what T high and T low would be, I can plug it in here. I'll end up with two equations, which says, on one equation says that 6 times 10 to the minus 4 has to be 0.7 times RA plus RB times C. And then T low is 4 times 10 to the minus 4 equal to 0.7 times RBC. This is, now one thing you notice, we have two equations, 3 unknown. This is called an under constraint equation. We have more, we can come up with infinite number of answers. Typically what we do, since resistors are easy to find, we just pick a C. And I say, okay, C, one is pretty common to pick a C. So let's say I pick a C that's 1 microfarad, let's say. Okay, and that is 10 to the minus 6. So as soon as I pick this with this equation, I'm going to have to deal with it, which basically says RB has to be equal to 4 times 10 to the minus 4 divided by 0.7 times 10 to the minus 6. So if I do that, then I will have my RB figured out. So if you do this work, we're going to get this to be 571. So we get this to be 571, and that's an ohm. And then we'll take this number, and we'll plug it in the first equation. That gives us 6 times 10 to the minus 4 equal to 0.7 times RA plus RB, which we know what it is 571 times 10 to the minus 6. We'll do a little cleanup on this one. We're going to have 6 times 10 to the minus 4 divided by 0.7 times 10 to the minus 6, and then minus 571 is equal to RA. We just kind of take things around and do the calculation, figure out what R. So once you do your calculation, you will find out that RA is equal to 286 ohms. So having done this, we have all the information we need to build our new circuit that gives us 1000 hertz per second. RA and RB, RB is 575, the other is 200 and some odd numbers, and I don't remember, so let's look it up. 286, and the capacitor was a microfarad. So we're all good to go and build it. Again, remember, when you're doing this circuit, the biggest, most common error is people forgetting that one has to be grounded. Everything else is on the schematic except for that one, and people forget to take a look at it. That brings us to the end of the precision timer work.